Okay, today we're going to go over speed time graphs. Okay, that's going to be our title, speed time graphs. We have to be able to do three things today, and you don't have to write this down, but these are the three things we have to do. We have to be able to calculate acceleration, interpret speed time graphs, and last of all, we have to be able to find or calculate distance. Okay, again, you don't have to write this down. This is going to be relatively easy. It's very similar to what we've done before. Same thing here, pretty easy. However, this is going to be a little bit challenging because we have not done this before. So let's go on to number one. Number one is how do we calculate acceleration in a speed time graph? Okay. Before we do that, let's look at a speed time graph. So in a speed time graph, we have on our y-axis here. So on our y, we have speed. Typically in meters per second. I mean, it's not always the case. Sometimes it could just be, it could be some type of different speed, like kilometers per hour. And then here we have time. This typically is in seconds. Okay, so that's what our graphs look like. How is this different than what we've done before? What we were doing before were distance time graphs. Okay, don't get this confused though with what we're doing today. These are speed time graphs, different things. These show, we'll go over what they show, but this shows the speed of a car. This shows something different, okay? It shows speed, but it shows something else as well. All right, let's say we have let's draw a quick sketch of a graph here. Bottom will go, which is time, will go by 5. It's 5, 10, 15, and 20. This will be our time in seconds. Okay. Here up on the y-axis, I'm going to go by tens. 10, 20, 30, 40. This will be our speed. Okay, in meters per second. It's not position, it's speed. Okay. So let's say someone goes from 0 meters per second to 20 meters per second, all of that in 5 seconds. So it looks like that. That's what the first part of the graph looks like. Then they go from 20 meters per second to 30 meters per second, but it takes them 10 seconds to do that. Looks like this. Okay? So if I ask you to calculate acceleration for these, well, we should remember that acceleration equals my change in velocity, final takeaway initial. Change is often represented by this triangle with the little shade on the side. That's called delta. That just means change. So my change in speed divided by my time, right? So my change in speed is here and my time is here. So if I divide this by this, that's just rise over run. Same thing as when we're doing the distance time graphs, right? So my acceleration is just slope. Same thing as before. So that's why I said that first part is probably easy. So it's just the same thing as rise over run again. Okay, so let's say this was A and then this was B. And I wanted to find the speed for them, right? So let's, not the speed, the acceleration. How fast is my speed changing? Well, for this first one, for part A, my acceleration would be my rise, which was 0 to 20. So it's just 20, divided by my run, which was 5. 20 divided by 5 gives me 4 meters per second squared. Very similar to the other graphs we did. That's why I'm kind of going over it quick, right? But what about for B? Well, for B, I rose starting at 20. I went up to 30. So that means I rose only 10. My run was, I started at 5, went up to 15, so I went 5, 10. So I went 10, right? So it's 1 meters per second squared because it is acceleration. So that's how you calculate acceleration. It's just a slope. Same thing we've been doing, right? And if it was negative, if it was going down, it would be negative, which just means it would be slowing down, which we're going to go over next. All right. So let's continue on. and go on to the next couple things I want you to do. So let's go on to number 2. Number 2 is, how do we interpret these graphs here? Well, let me create a quick sketch of a graph for you. Very simple one. We'll go 5, 10, 15, 20. Probably should be spaced out more equal, but it's fine for the purpose of this. 10, 20. Okay? This is time, meters per second. Alright, let's create a quick graph here. Let's say we travel, looks like this, then it looks like this, then it looks like, let's go all the way up to 15 here, and then back down. So just keep it simple, okay? Alright, so if you see a straight line like this, that just means our acceleration is not changing. In other words, we have you can say uniform. Uniform means stays the same. Uniform acceleration, or you can also say a constant acceleration. Okay. All right. Now let's think about what's happening in this middle line here. This middle line here, I'm color it blue now. I'm just going to distinguish it from the other one. So our first thought is, in here, this person is not moving. But that's actually not the case in these type of graphs. Because if we look at this graph tells me that at 5 seconds, he was going 10 meters per second. And then at 15 seconds, he was also going 10 meters per second. In other words, he just stayed at that same speed. He didn't accelerate. So what does a straight line mean? It means constant velocity. Okay? So constant velocity isn't always 0. The speed stays the same. Another way to say this is no acceleration. Okay, so they're not accelerating at all. That's another way to say it. So no, let's just put that there. No acceleration. We'll abbreviate. Okay, no acceleration there. Okay, what does a negative line mean? Well, if slope equals acceleration, and if we get a negative slope, means we have a negative acceleration. Well, we already know what negative acceleration means. That just means slowing down. Okay? This doesn't mean we're going back to the origin. It used to mean that in the distance time graphs, but this is showing us how a car accelerates. So a negative slope would mean slowing down. Okay? And then last of all, what you should have seen in the last graph, which was the previous graph we just did. The higher the slope, the faster the speed, the faster the acceleration. The lower the slope, the lower the acceleration. Same thing to when we did speed, right? Lower speed equals lower slope and so forth. So again, if this is a graph and we have meters per second here, and we have time here, right? And we have two lines. We have a line that goes like that, and we have a line that goes like that. Well, higher slope just means higher acceleration. Okay? What does that mean? That means our speed is changing faster. What does that mean in like real life? Well, think about a car. This would mean like I'm pushing the gas real hard and we're going real fast, so we're changing speed very fast. Whereas this line here, I'm pushing the gas and we're speeding up, but we're not speeding up that fast. Okay, so that's what it means. All right, so we've just knocked down those first two things. Now we have to go over the last part, which is 3. Calculate. How do we calculate distance? Okay, so again, we're trying to calculate distance. Let's think back to when we first started this class and we looked at our speed triangle. Speed equals distance divided by time. Okay, so you should have known from this or from the past, we already know that distance equals speed times time. Okay, so I'm just going to leave that there, and we'll come back to it, but we know that already, correct? All right, so let's look at our graph here. I'm going to make a graph just to copy this. It's going to go 5, 10, 15, 20. Let's go extend it here. Okay? That's time. Then we have on this other side here, go by 5s as well. 5, 10, 15, 20, 25 meters per second. This would be seconds. Okay? All right, so let's say we have a graph that looks like this. In 5 seconds, it goes up to 10 meters per second. It stays at 10 meters per second for 5 seconds. And then finally, it travels about 20 meters in 20 seconds. Okay. All right, so our objective is to find how far we've traveled in each part. So to find out how far we traveled, usually we would just look on the side and the side will tell us, right? But these graphs don't tell us distance, they tell us speed. However, let's look at these, let's break it up into segments, A, B, and C. Okay? Well, if I'm looking at B, B went up 10, which is my speed, right? And it went to the right 5. So it was 10, and it was 5. Okay? Well, I know distance equals speed times time. In other words, speed is 10, and this is my time. So if I just multiply these, that would give me my distance, right? But what is that? This times this? Well, that's a shape. That's basically, if I multiply these, that's going to give me my area. Okay? So in other words, my distance just equals the area under the graph. Okay? So if this confused you of how I explain this, just all you really have to remember is that distance equals area under the graph. Okay? All right, next thing we have to know is that area changes, though, depending on what shape we have, right? So if I have a square or a rectangle, my area equals my height times my width. But if I have a triangle, which is really the only two shapes we're going to deal with, I still have my height and my width. But if you notice, it's about half of that, right? So it's still height times width, but you multiply it times 1/2. Okay? We'll go over how to do that too. All right. So let's go ahead and solve for this. Let's do it for two of them. First, let's find how far did he travel in section A. Remember, I want to find this area here, this red one. So for section A, my height was 10. My width was 5 times 1/2. What does that equal? Well, 10 times 5 equals 50. Let me actually keep writing. Let me write that. Let me write this here. 5 times 10 equals 50, right? 50 times 1/2. All right, how do you multiply a fraction like this? Well, all you really have to do, this is the same thing as multiplying, because 1/2 is just 0.5. So it's the same thing as multiplying times 0.5. Or you can just divide by 2, okay? So if you put that in your calculator, you would go something like this. You would go 50 divided by 2. It would be 25, okay? So it's 25 meters because it was distance, okay? That's how we solve it, by calculating the area. Do I always multiply times 1/2? No, only when it's a triangle. So let's look at B. So for part B, if we want to find how far he traveled, it would be height, which is 10 times, well, he started at 5, went to 5. This here, this base, my width is 5. So it would be 50 meters. Okay? He traveled 50 meters in that time. So that's how we solve distance, which is difficult. Okay? It's a little bit more difficult, but I think we should be fine to do it. All right. Let's go on to the last. We're going to work through an example here. Okay? So here's the example. So you should have this copied down in your notes already. Okay, let's go over some things. First, let's go over calculating acceleration. That's easy, right? What's the acceleration from part A to part B? Well, from part A to part B, from A to B, my acceleration would equal, I went up 10, and I went over 10 as well. So it's just slope. 10 divided by 10. That's 1 meter per second squared. Okay? What if I want to find the slope or what if I want to find the acceleration of this part here? Let's go ahead and do that. Okay? So I'm just working through some practice problems so you guys can see how it's not too difficult because we've kind of done this before. What's my acceleration here? Well, if you notice here, I went down, I started at 20, and I went down to 0. So I went down to it's negative 20. I was at 35 and I went to 40. So my run is 5. So my acceleration is negative 4 meters per second squared. Negative 4 meters per second squared. Okay. That's how we do acceleration, not too difficult. What about interpretation? What's happening here? Well, if I were to ask you what's happening here, you would say he started at a speed of 0 and he accelerated uniformly to a speed of 10. What's happening from B to C? He stays at a speed of 10. What's happening from D to E? Well, he just stays at a constant speed of 20. In other words, no acceleration. What happens in E to F? Back to the origin? Nope, that's not what it's telling us. It tells us he is slowing down. How much does he slow down? Well, he slows down from 20 meters per second all the way down, slows down to 0, comes to a complete stop. Okay, so what happens here? He comes to a stop. There, that's part 1 and part 2. Now let's go over the last part, calculating distance. How much distance did he travel? So let's go ahead. Let's do that for 2 segments. Let's do that for this part here, B to C, and we'll do it for E to F as well. Okay? All right. So if I want to find how far, so we're going to find our distance from point B to point C. So how much did he travel in his car? Well, again, we're trying to find this area if we're trying to find distance. Okay? This is a rectangle, so I'm just going to go height times width. Okay? Well, my height is 10. So my distance traveled here, my distance traveled is going to be, actually I don't want to put this, I don't want to confuse you guys. Let's just go, let's just write it out. My distance from B to C would equal 10, which is my height, times, well, this is also 10, right? Because it's 5 and 5. So my base, or my width, is also 10. So it would be 10 times 10 would be 100 meters. Okay? 100 meters. So that's how we do, that's how we figure out the area covered, or the distance traveled. Let's do the last one. What if we want to find E to F? In other words, I need to find this area here. Okay? Well, from E to F, that's a rectangle. So I'm going to go height, which is 20, times my width, which was 5. But I can't just go 20 times 5 because it's a, sorry, that's a rectangle. Because it's a triangle, I have to go times 1/2. Well, 20 times 5, that's 100. So it's 100 times 1/2. In other words, times 0.5 or divided by 2. Either thing is the same thing. So if I divide 100 divided by 2, would give me 50. So in part E to F, I traveled 50 meters. Okay? So if you can do everything that we just did, then you're fine. Let me put this up for you guys. You can see.